on this, the idea or the objective of this session will be to understand the basics of group theory and binary operations. So first we need to know what is a binary operation. Then here when we come to the definition, for a binary operation, we see that we're going to be looking at cases of a star. Sometimes it will be a hash, sometimes it will be this O. It will depend, right? So it can be anything with binary operation. So it can be represented by anything other than plus. So we can't represent binary operation by these ones, you see right now, but we can represent binary operation by any of these. So now we look at a star as a binary operation. We say that a binary operation star on a set G is a rule assigning each ordered pair of G's elements to a unique element in G. Or in other words, we are saying that this is a mapping. We're saying that a binary operation star. In other words, I'm saying that this is a function, right? Such that G cross G maps to G. So, yeah. So, when we come to define this, we can say that a binary operation can be commutative, right? We're saying that a binary operation star on G is commutative if A star B is equal to B star A for all the elements which are A, B in G. So if we take these two elements in G, then we compute them, we're saying that this will be commutative. It will be commutative. So now we come to say that also a binary operation star on G is associative if we take A, B, C from G, and then we have A star B star C with these brackets. Then if now we shifted the brackets to BC, which is this, right, we say that now this is associative. So when we look at commutative, guys, commutative, we shift these statements of their positions. We just swap them, you see, right? So you see that I swapped these statements, these two statements. That's why we realize that now this is commutative. But the moment you shift, you have three elements and you shift brackets. Now that is called associative. Even if you have more than three elements, as long as you shift brackets, that is called associative. But the brackets should be shifted between two elements. So now we come to identity and inverse. So all these that I'm looking at now, commutativity, associativity, identity, inverse, these are going to form to form a group and also an abelian group. So when we come to identity, guys, and inverse, so let's look at an identity. We are saying that this identity element will be denoted by E. Most cases this is denoted by E. We're saying that an element E, element of G, is an identity for this binary operation star if A star A is equal to A star E is equal to A. In other words, let's say now our operation is multiplication. If I take A times this, which is equal to A times A, which is equal to 1, which is equal to A. So this would mean that we know that according to multiplication, the only number that you can multiply by A and still get A, it's 1. So it means that our E here would be 1. You see, there are cases where you'll be forced to find E. You see right now, there are cases where we'll be forced to find A. So you must know that in this case, on multiplication, by default, it's 1. The identity of multiplication is 1. And also the identity of addition will be 0. So it means that this would be 0 plus A, which is equal to A plus 0, which is equal to A. You see, right? So we'll see when we come to questions that require us to find this. So, but this is not always the case. Most cases when you're dealing with matrices, the identity can change. You can find any number that is an identity. So, but this is just a default identity. You see right now. Then when it comes to definition of an inverse, we're saying that for star G on for star on G with E as an identity, right? And we take an element B from G, which this we are saying that then this will be A's inverse. In other words, you're saying that B is the same as A. In other words, I could replace this B by A. Let me see, let me take a pen. I could replace this by A steric, right? Or you just put A this, but it's preferred to use this one. Or you can use A inverse. For multiplication, we use this. But when we use this one, it can represent multiplication and addition, so that we know which one we're dealing with. So if you don't know which operation it is, you just put this one. It will be fair, right? But here you can also put B. It's also fine. So we are saying that if we have star on G with E as an identity, and we take B from G as A's inverse, right? Remember, we have here G cross G moving to G, and from this G we take what? We take B. Let's say we take from 1G, right? Or I could suppose that we're just having this, then I take B from this to say that this is the inverse of A. Then if I apply the binary operation between the two of them, the answer between A and its inverse should give us an identity. You see, right? So in other words, let's say the operator now is plus, and I have A. You know that the inverse of A in addition should be minus A. And if I apply commutativity, here I'm going to get 0. And we know that 0 is the identity of addition. And for example, if now it's against multiplication, I take this inverse, the answer here should be 1. We say, right? So now we see that that will be the case, or an inverse. Now, since we have looked at these elements, I can go back to the binary operation and say that if we take elements from this and then we apply the binary operation, we find that those elements are found in G, right? Then we say that there is closure. You say, right? Now, when we come to a definition of a group, we are saying that a group is a set G with binary operation. Now you see that I said that binary operation can change. That's why here I chose a different operation, right? Satisfying. First rule, it should satisfy closure. Once it satisfies closure, let's say I take G and H, I apply the binary operation. I found that these are in G for all G, H element of G. I took this from G, apply a binary operation. I found that they're in G. So since I apply this, now it means that closure is satisfied. We say right now. Then I come to the second rule. This is associativity. Now for associativity, I want to remember I said that for associativity we're gonna take 3 elements from G. When we take these 3 elements from G, we apply GH and K. We say right with this brackets here, and we find that it's equals to the other side where I shift brackets to say this. Let me write this is in GH. Now when I shift the brackets to here, which I get this side, if these sides are equal, then we say that this is associative, right? The binary operation is associative. Then now we can have identity. Remember for identity I said that this, if we take E from G and it exists where G binary operation E is equal to E binary operation G, which gives us G, then we say that there is an identity. E will be the identity for that element. Only if when you compute it with that identity we get that same element, right? And that will be G as the element that will be computed by the identity. Now when you come to the inverse, for the inverse case, remember I said that if you know that you can also take this, right? Remember I said that you can also denote it like this. So for the inverse, if I take G from G and H from G exists, meaning that this H is an inverse of this, right? With I take G and H, I apply the binary operation with commutativity, then I get E. It means that this is the inverse, and it can be denoted as, you can say that H is equal to this. You see, right? If this is in multiplication, you can represent like that. Then now, if commutative, we check this with a group. For a group, guys, only these four should meet this. Only these four should satisfy the binary operation for this to be a group. But the moment the fifth one is satisfied also, now we call this an abelian group. The moment commutativity is satisfied, if we take G and H from G, then we apply the binary operation to say that G binary operation H is equal to H binary operation G. We say now this is an abelian group. So these are the terms that we're going to be using throughout, right? The lecture. So now, if all these 4 plus this one is satisfied, then we say now commutativity holds. You say right now, if those 4 plus this one, if there are 5 and they holds, then we say that this is an abelian group. But if only this 4 holds, we say that is a group. So you see that we know what is an abelian group, we know what is a group. So let's come for an example now. Let's say I apply closure and I find that this closure is not satisfied. The moment closure is not satisfied, automatically the rest are not satisfied. We are not going to check the rest. You see that? If they say check if this is a group or show that this is a group and you find that closure is not satisfied, or you start with something else other than closure, you'll be wrong, right? You should always start with closure. Check. If I take 2 elements from G, then I apply the binary operation. Are those elements still going to be found in G? You see, if yes, then there's closure there. Then you can apply the rest. If closure is not satisfied, then this is not a group. If one of these is not satisfied, it's not a group or an abelian group. You see, right? So if there's no identity, there can't be an inverse. You see, right now? So these two, actually the inverse depends on the identity. If there's no identity, it means that there won't be an inverse. So must be certain with that. So examples of binary operations, remember I said that these are also binary operations. Plus is a binary operation on Z. Reason being, if I take, let's start with closure. If I take 2 elements from Z, let's say if I let A, B be element of Z, then I apply closure, right, with plus. I take A plus B. If I take A plus B and I found that A plus B is Z, obviously when I take 2 elements, obviously 2 elements are going to be in Z. You agree right now? Hence, there's closure here. Then I come for associativity. For associativity, I'm going to let 3 elements, let A, B, C be an element of Z. Then, if I show that A plus B plus C is equal to A plus B plus C, then we know that associativity holds. And we know that with integers and addition, it doesn't matter how you add them. At the end of the day, they're going to have the same answer. You see, right? As long as the numbers are the same. So if A is 3 here and A is 3 here, and then here B is minus 2, here B is minus 2, C is 1, C is 1. Doesn't matter how you add them. Doesn't matter the order. The matter of the fact that at the end of the day, they're going to give you the same answer. Then associativity will hold. Since there's closure, there's associativity, you can come and check for identity. Right? With identity, if I let A be an element of this, right? And I take again minus A as an element of G, right? And then, not minus A, this one is for inverse. Let me say this is an element of Z. Then, if I say, or maybe it's 0, right? If I say, but I can take E and then start solving for E. Then if I take A plus E, which is equal to E plus A, which is equal to A. I can solve for E. I can find what is E. Then, how do I solve for E? I can even take this part only, right? I take E plus A, which is equal to A. Then I take A to the other side, meaning that A will be equal to 0. Ask myself, is 0 found in Z? Yes. If I take any number plus 0, it will give me that number. You see, it means that this is the identity. I found the identity, therefore identity exists here. Since I have the identity, I can come and let A be an element of Z, and also let minus A be an element of Z. Then I take these two, A plus minus A, which is equal to A. And our A is what? Is 0 there. Then I get that A plus minus A is equal to 0. Then I take one thing to the other side. I know that minus A will be equal to minus A. And this is true, right? Then this we know that is the inverse of A. Then since the inverse is met, identity is met, closure is met, associativity is met, then I can say that this is a group on Z. You see right now? But we know that this is a binary operation, right? So we know that this is a binary operation. And when they say minus is not a binary operation on Z, but on Z plus, we can check that. Let's say we check on Z plus, right? We say Z plus, remember Z plus is that here, it's like a natural number. So if I write like this, I'm sure you're going to understand. These are numbers until infinity. You see right now? And then, when I come here and take, let's say I take 1 minus 2. I take two numbers. I let let 1, 2 be an element of Z plus. I want to check closure. I take A 1 minus 2. I find that this is minus 1. This minus 1 is not an element of Z plus. So this is not closed. Therefore, this is not a binary operation. Remember, binary operation says that if we take a binary operation, let's say in this case we take minus, right? On G, here that says Z, right? So here, let me just say G cross G going to G. So here our first our domain here is Z plus. You see, right? Took this from Z plus, we're going to Z plus. We check. We took these two elements from here, but you realize that the final product is not in that element. You see, right? So this cannot be closed. So this cannot be a binary operation. Now I'm sure we will get this, right? If we do, then it will be simple when it comes to practical part. Here I was just showing some few examples that we can look at. So now we can look at this. So what we looked at, first we looked at a binary operation on a set of G, which maps pairs of elements to a unique element in G. When we say that a unique element means that when I apply a binary operation or add two elements or subtract two elements or divide two elements, I must get one number. Then that thing is a binary operation. The moment I get two numbers, that is not a binary operation because the output is not unique. You see right now. Then no, for a group, we know that a group, for something to be a group, it requires for it to be closure, associativity, and also identity followed by an inverse, right? The moment that all these four are satisfied and then also commutativity is satisfied, then that group is called an abelian group. So we will only look at an abelian group and a group. But as time goes on, we're gonna be looking at things like homomorphism group. I'm sure you've seen this from algebraic structures. It's either it's from that chapter of set theory, right? Homomorphism group, isomorphism group. So we're gonna be looking at these as time goes on. Then we're gonna be looking at a monomorphism group. So monomorphism group is a group that this one it satisfies one-on-one. It's if G is one-on-one, then it is called a monomorphism group. Right? this one is called a monomorphism group. Then we're going to look at the other groups that you will come across. So this will be simple because I believe that this is straightforward. The moment you start to understand what type of a binary operation do I apply here. So when we talk about, one thing I can tell you, right, when we talk about a homomorphism group, here we're just gonna be looking at a group, right, that has two operations. It can have times and plus. You see, right? If I take two elements, let's say I take A and B, right? Then I say, let's say I have 5. Then I apply this function on A times B. I find that this is equal to 5A plus 5B. You see, right? Or instead of having a group like this, I believe that this one could be most complicated group, right? If I have something like this, let me say I have something like this. I have G2. Okay, let me also include some. I have a group G which maps to a group G prime with operator plus. So if I take two elements from this group, let's say I let A, so here I can just let a 5 be a function such that we have this group to that group, right? So I take A, B, which is an element of G, from this group which has a binary operation of multiplication, right? Then I take the function, apply the function of A times B. Then I find that the solution here is phi of A plus phi of B. Then therefore I can assume that this is homomorphism. The moment I talk about isomorphism says that a group should be, this function should be 1-to-1 and it should be onto. This is meaning it should be bijection. The moment a group is bijection, we call it isomorphism. The moment a group is 1-to-1, we call it monomorphism. You see, right? So we're going to be looking at this as time goes on to say that these are simple. They're very simple. They're not that difficult. So now, yeah, I thought we're going to do this first one. Then let's look at the second slide, right? We can look at the second slide. Then we'll look at some problems there. When we look at the second slide, yeah, now we see that on the second slide, we're going to be looking at functions, the function compositions and properties. So here, not necessarily that, but we're going to be focusing on doing these exercises, right, that we have here based on what we did. So we have the first problem, 0.2.3, right? I took this from the guide. So now here, we are given this. They say that we should apply function compositions. They say now the problem statement says that let phi beta and rb maps from z to z. So this is defined from z to z. Then they say defined by phi of n is equals to 2n, beta of n is equals to n plus 1. Then r of n is equals to n squared. So defining this, we realize that here they say that we should write a formula for each of the following compositions. So the question is, how do we write compositions? Who can tell me, who remembers how do we write compositions? Sure, you have learned this. Remember composite functions, right? Yeah, I just wrote it as function compositions. Do you remember composite functions? Anyone who remembers composite functions? If you remember composite functions, you can maybe try to say, this is how I write this problem. Anyone who still remembers how we write this? Anyone? We can try to say this is how I write it. If you still remember, you can try. Yeah, but if not, I can do this, right? So let's check. Our phi is defined by n. They say phi of n is equal to n. It means that when we define this composition, we're going to say phi. So I'm taking this phi. You see right now? So I put it inside. So I'm going to say phi of phi n.
Doctor, let's for disturbing you, but then I try to write how I write a composite function there in the comments.
You wrote in the comments?
Yeah.
I'm gonna try. I can't see the comment sections. I'm sure you can see on my side.
Yeah, go to in-call messages.
Yeah, ne?
I don't know if it shows now.
Oh yeah. FG of x is this is how you write it. Yeah, this is how you write it. Yeah, it's correct. So that's how we're gonna write it here. So we're gonna write it like that. Giving it that many ways you can write it, but we're gonna use how you wrote it there, right? The other way says it depends on which side you take it from. Other way says that, let's say I have this, I have phi beta, right? X, not even x. Let me say this. Others, they prefer. Let me put x outside. I want to show you the difference between two composite functions, right? This type of composite function that you can write it like this. This one you can say this is phi beta x, right? Some, when they take it from the other side, you will see this if you're going to be doing final level writing. There's what we call taken from the left, also taking it from the right. Some, they would prefer having it like this, right? But us, the one which we're gonna use is this one of taking it as it is. So whatever that is on the right, we're going to put it inside. You say, right, this is always gonna be inside with us. We say right now. So this is the approach that we're gonna be using. What you wrote in the comment sections. So now, according to that, remember our definition of phi is phi n. So we're gonna take phi n, put it inside this one, right? We put it inside. We say that this will be equals to, and phi n is equals to what? 2n. We agree here, right now? So, in other words, what you do here, from here, according to binary operation, says that whatever that is inside here would be plugged where we see n. You see now n is replaced by 2n. We agree right now? So it means that this will be equal to 2n. It's like this. It's like if I have, remember from first principle, if I have f of x is equal to 2x, but if I have f of x plus h, wherever I see x, I'm gonna plug x plus h. We say right now. This is the same composite function we're using in first principle. So now our phi changed to phi 2n, and those who want to know how did I get to phi 2n, let's check this. Phi n is equal to 2n. So there I just substituted directly. Then if we check this one, that's what we're gonna do also here. We take this, we say phi n. You see right? This one, we say alpha beta n. You see right now? And then this one, this is simple because they're both beta, right? So you wouldn't make a mistake here. Then this one, n. You see right? Then this one, n. And then whatever we have inside, it's there, it's defined. We're just gonna plug. Then this would be 4n. Then this would be, and this one is for phi, right? It's 2n. Phi is 2n. then this one is defined as n squared. So it means that within n we're gonna put 2n, and this will be 4n squared. And then for this one we have 5, and beta n is defined as n plus 1. So this will be, and phi is defined as 2n, right? So within n we're gonna put n plus 1. So this will be 2n plus 2. We say, right? And then d, we're going to say this is beta, and we know that beta is defined as n plus 1. There, right? You can see it's defined as n plus 1. And then this will be equals to, beta is defined as n plus 1. So when we see n plus 1, we're gonna put n plus 1. You see, right? There on n, apply the n plus 1. The other one is coming there. You see, right? From the equation. So this would be n plus 2. This will assist us when we are going to apply associativity, closure, on those other problems, right? That will be coming across next. So now this is beta. We know this one is n squared. So here is beta n squared, which is equal to beta is defined as n plus 1. So this will be n squared plus 1. Right? Then this will be is defined as n squared, and this will be inside the n is like square, like that, n to the 4. Then this will be the solutions to this problem. Now when we come to, now let's do this. When we come to now this problem, if you have any question on those ones, guys, you can ask, right? Then yeah. Now here they say that we must yes.
Can you scroll back? I want to ask something.
Yeah.
No, yeah, you can scroll. I think it's on E. On D.
On what?
Isn't supposed to be on D, number D.
Yeah.
Wasn't it supposed to be n plus 1 times n plus 1, since it is D, and then we have bn inside?
N plus 1 times n plus 1?
Yeah. Are you not substituting B with that n plus 1?
Yeah, I get it.
The one who is which?
Check. I get a bn is n plus 1, right?
Yeah.
This is fine, right?
Yeah.
Then we come now here. We say now this changed. It's no longer n. It's n plus 1. It means that we'll replace this by n plus 1. If this n inside here is replaced by n plus 1.
Oh, okay.
And then we added that remaining one. Is that right, ne?
Okay.
Yeah.
Okay.
If you have any question, guys, please ask. These are the most important parts, right? So your test one is gonna be formulated out of these things. So now we come to these injections, surjections, and bijections, right? We know what is bijection. Bijection is when a function is both surjection or injection, or I can say when a function is both one-to-one and onto. So for this one, for injection, who can tell me, is injection one-to-one or onto? Who can tell me, is injection one-to-one or onto? This one, is it one-to-one or onto? Didn't I put didn't put the definitions there. Is that one-to-one or onto? This is what?
It's one-to-one. Previously one-to-one. Previously said that it's one-to-one injection.
It's one-to-one, right? So
yes.
Since we know that injection is one-to-one, then one-to-one says that if we have, let's say here we're given a function, we're given this, they say f such that n, we have n which maps to z, right? Such that this is defined as f of x is equals to 2x. For us to check that this is 1-to-1, we must come and assume, what? That f of x is equal to what? F of y. If we let x, y be an element of a natural number. Right, ne? And f of x is 2x, f of y is 2y. The aim is to show that x is equal to y. We agree, right, ne? Then if this is the case, therefore f of x, or I can say therefore f is we say right now. For us to check if this is injective. Do you agree here?
Yes.
And then, for us to check if this is, say, surjective or onto, we must take an element from the codomain. We let y be an element from the codomain. This is going to be, say, D, the codomain. This is from SMTA022 and SMTA022 right? Be the codomain Z, right? And then, since we have this, we said that we let y be the codomain, right? And then we let f of x be equals to y, be equals to 2x. And then we solve for x. And then when we solve for x, we are going to say that x will be equals to y over 2. Now we check y over 2. Is y over 2 a natural number? Agree why I took it from z, right? Let's say from z I took 1. Is 1 over 2 going to be a natural number? Is 1 over 2 going to be a natural number? Guys, is 1 over 2 a natural number?
No.
No. Therefore, this cannot be surjective. So I'm going to say, therefore, this is not an element of a natural number. So in other words, for surjective, right, which is onto, when I take an element from the codomain, right, when I take this element from the codomain, then I equate it to f of x. The aim is to solve for x and check if that x is found in the domain. If that x is found in the domain, therefore we know that this is surjective, right? Ne? Therefore we know that this function is only injective. So since it's only injective, it cannot be bijective. We agree, right? Ne? So because bijective, it should be both surjective and injective. So now we can check the B. So we can check B now. Let me erase this. We can check B. With the B, we have x minus 4, right? And then here we're just going to take two elements from Z. Then when we take these two elements from Z, right, we say that now here, this is going to be, we say f of x is x minus 4 and f of y is y minus 4. Then we say that now if I take 4 to the other side, I'm going to be left with x equals to y. Therefore, we know that this is what? Injective. But this is not, this is our least concern, right? Now let's check for surjective. We let y be an element of z, this one, right? The codomain. B, the codomain. Then we let this be the codomain z, right? Then we let y be equals to f of x, which is equals to x minus 4. Now from here, we see that if I solve for x here, this will be that x will be equals to y plus 4, and this will be an element of an integer. If we take, remember y is an integer. If I take an integer, any integer, then I add 4 to that integer to remain an integer. If I take 3, I add 4, we'll get 7. 7 is an integer. So this is both injective and surjective. So it means that this one is bijective. You say right now. Then we come to B, to C. With C, I'm gonna do C right yourself. You're gonna do D. We take C now. We let X, Y, Z. Yeah, this be an element of N. This one now. This is based on N. This be an element of N. Then this will be X squared plus Y squared. Now check this. For this to be injective, the x and y should be unique. Now check this. When I square root both sides, this I'm going to get plus or minus x plus or minus y. The moment you have this, these are no longer, this is no longer injective. The moment you have plus or minus there, this is no longer injective. Because here it's possible that x can be equal to minus y. If these are equal, they can still give us this. You see, right? But this does not necessarily mean that x is equal to y. You see? So this cannot be injective. The moment you have plus or minus, you find yourself having plus or minus, this cannot be injective. And then we check surjective on this one. We let y be an element of n, this one be the codomain. Let this be the codomain n, right? And then we now say let y be equals to f of x, which is equals to x squared. Now I want to solve for x, right? Which here, if I square both sides, x will be equals to plus or minus root of y. So this one, also the element is not unique. We say, right? The element is not unique. So when we check this, now we check and say that this will be, if I take x equals to plus or minus root of root of y. This we're going to say that this is not an element of natural number. Reason being, check if, let's say I take even if we forget about the plus or minus, right? Let's say I take 3 here from y. When I take 3, I'm gonna get root of 3. Is root of 3 a natural number? Is root of 3 a natural number?
No.
No. So it means that this, but the moment I saw by having plus or minus that this is not unique, so I won't be having surjective here. So this is both, is not injective and is not surjective. Hence it won't be bijective. You see right now. So that's what we get for this. So you're gonna try D and see what you get there. Now, if you don't have any question, we can come to the last part, right? These ones, these are gonna be there. You'll see even when they're going to teach you binary operations, don't dwell more on these questions. But since we understand the previous part, and these are coming from a tutorial, right? So they might even try to take and give you a tutorial, a quiz to write about them. So, but usually on this one, they don't, unless if they change this here, they don't focus more on the guide, right? Even though they use it, but setting, they don't set with the guide, they set with textbooks. So, which of the following define binary operations on the set of integers? So here we're defining this on set of integers. We must keep this in mind. Then of those that do, which are associative, which are commutative, and which are idempotent, right? So now what we're gonna do first, we're going to check if this thing is closed, right? We're going to check if they're closed. So in other words, we must check if these are binary operations, right? or they define a binary operation on set of integers. So let's say I come to A, I let M and be an element. I'm going to take whatever they gave me then of an integer. Then I apply that MON is equals to MN plus 1. We agree here, right now? And then we check, is this an element of an integer? Is this an element of an integer? If I multiply two elements, then I add 1. Will they still remain in integers?
Yes.
Yes, so this is an element of an integer. Therefore, closure holds. So the closure property or closure law is satisfied. Therefore, if closure law is satisfied, it means that I can check associativity, commutativity, and idempotent for that element. You see right now? So since closure, let's first check closure for these elements and see which ones are we gonna confirm if they hold. Now let's check here. Let's check on this one. If I'm taking those two elements, let me use that. If I'm taking those elements and let me give a message. I check this one. Alright. Is let's say I take two elements, I add them, then I divide by 2. Let's say M is 1, N is 2. I'm gonna get what? 3, right? Is 3 divided by 2 an element of an integer?
No.
No, so this one closure does not hold, so I don't have to check associativity, I don't have to check idempotent for that one. You see, right? But you can, but I don't have to, right? Then we come to this one. C. I take M, I take N, which is equal to M. And since M, I took it as an integer, M won't change with the remaining itself, so this was the remaining integer. So this one satisfies closure. We agree right there. So here the binary operation is defined on this two. Then on this one also it will be defined, because here I'm just squaring a number. You see right now? So this will be defined also, the binary operation. E, I'm squaring both of them and add. This is also defined. Then F, it will remain 3. 3 is an integer. We agree right there. So those ones, they are closed. So these are integers. We agree right now. So the binary operation is defined on this, on A, C, D, E, F. So the first question should be A, C, D, E, F. You see, they said what? Of those that do. It means that only those that are here we can check associativity, commutativity, and idempotent. You say right now. Then of those that do, we must check. So even if they didn't say this, you must just know now that if closure is not satisfied, why am I checking associativity? Because obviously, whatever that will be associated with, it might not be within the same set. You say right now. So it will be pointless. So let's check the first one, A. We check associativity first. So when we check associativity for this one, for A, we're going to let 3 elements. We let the ones which we have there, M, and then we add one special element, P. Always add P right now if we are given M and N. So here I'm saying that if I have M or N or P, let's check what this is equal to. So I'm not gonna. I remember that in most cases from first level you used to do this. You just write this, right? You used to just write this. Then you check them one by one. Now you're not allowed to write this. You're just gonna write one side. You check it. We know already that MON is also what? MN plus 1. We agree, right? So the first step is simple to plug. And then I put OP. So binary operation says this, guys. Check. According to this definition, M is now represented by this. Do you agree with me there? You say right now. According to this definition, M, the left hand side is represented by the left hand side, the right hand side is represented by the right hand side. So when you come to compute this now, we are going to say this will be plugged where I see M on this definition. Where I see M, I plug Mn plus 1. So on M, I plug Mn plus 1. Then where I see N, I'll plug P. You see right now? Then there I'm going to plug P. Then I add that one which I have there. Then I check. This is MNP plus P plus 1. Now let's check the right hand side. Inside is MONOP. Let's check. Now according to this definition, I can remember we always start with the inside right now of the bracket. According to this definition, N is represented by M. That is the one that comes first. Then P is represented by N. It means that where I see M, I plug N. So I'm going to have N here. Then on N, I have P. And that is plus 1. So let me just start with this one, which is here. This is this one right now. Oh, then inside there, I do what I was doing. This is represented by N. This is represented by P. Right? And then I write plus 1. This plus 1. So, now, this remains the same. I applied the definition. First one is represented by the first one. Second one is represented by the second one. So it means that this will be M. I plug M there. Then on N, I plug the second one. P plus 1. Then I added that one which is out there. Then this will be M and P plus N plus 1. Now let's check if these two are equal. This is the same as this, right? But P is not the same as M. Even though you say right next, so they differ there. So since MON or P is not equal to MONOP, therefore the associativity law is not satisfied. You say right now, so that law won't be satisfied. So now let's check commutativity. Let's check commutativity. For commutativity, we're going to let Mn, which is an element of an integer. Then we have MON. Here we must show that MON is equal to NON. Again, we are commuting. I remember how we defined commutativity from the beginning, right? Then here I'm just going to take one side first and I show it. One side is given that this is M n plus 1. Then if I commute these two, this simply defines that N O N. You see right there? Hence, we see that this is equal to this. Do you agree here? We say right there. Now that is commutative. It means that A is commutative. And then, if I want to define idempotent, for idempotent, I'm going to let M be an element of an integer. Then this will be idempotent says this is that I must show that MOM is equal to M. This is what it says I must show, right? So I'm going to first check MOM. Then I'm going to say this MOM is equal to. So let's check the definition is here. M is represented by M, so I'll write M. N is represented by what? By M. Then on N, I'll write M. And this is plus 1. But is this equal to M? Is that equal to M, guys? Is that equal to M? Guys? Guys, is that equal to M? Anyone who can tell me, is M plus 1 equal to M?
No, it's not.
No, therefore this cannot be idempotent. You say right now. It is only means that A is only commutative. It's not associative, it's not idempotent, it's only commutative. So yeah, I was not supposed to do these questions, right? I wanted you to do them. So now let's check C. I'll only check C and then you are going to check these three, right? Then you tell us what are these and how did you find them. So let's check associativity of that first, then we'll check the rest. Now we check associativity. We let three elements M and P be an element of an integer. And then we have MO and OP. Right? According to this is equals to M. It doesn't matter. Now check this, check the definition. The definition says that now we must check the relationship between this solution and the definition, right? Definition says that the answer is always the first element. Do you agree here? It doesn't mean that the answer will always be M, because this is not a constant, you see, right now? The answer will always be the first element. We agree, right now? We say this right now. So it means that when I compute this one, the answer here will be M on that one, right? Or P. And the answer here will always be M also. Again, we see that the answer is always the first one. Here the answer is M. I just plug the M in there because I know that that one is also M. Then when I compute this, the answer will also be M because M is the first element there. We say right. But now when I check this, MO, N, or P. This I have MO. Here inside the answer will be N because the N is the one that comes first. You see right now? So I don't have to put brackets. That is N. And MON, we know this is M. Hence here, we see that MON, OP is equals to MO and OP. Hence associativity law is satisfied. We see right now. So let's check commutative here. So first, we are given this. We are given MON. We know that this one is equals to N, the first element. Then if we check NOM, this will be equals to N. And these two are not equal. You see right now? Therefore, MON is not equals to NOM. So here I can't commute because the element is alone, right? If it was, I would commute. So this is not commutative. Commutativity is not satisfied. So here I was just gonna just let M and be an element of an integer. Now we come to check idempotent. Idempotent, we're just gonna let M be an element of an integer. Now, idempotent says that MOM should be equals to M. Right? Now let's check. MOM is equals to what? The first element is M, so this will be equals to M. Therefore, this thing is idempotent. Idempotent law is satisfied. You see right there. So, according to C, only associativity and idempotent are satisfied. So I want you to go do this D, E, F. Then this will be the, yeah, let me discard this because I think I've already, yeah. So yeah, if you have any question, guys, let me just stop the recording, right? If you have any question, you'll ask, then yeah, we'll see about it. So let me end the session now.